Right, let's see how this goes. It's a bit more complicated or difficult to do a video clip of a further maths problem than it is of a nice intermediate year GCSE. But this is how the information is set up and what it looks like on a graph. You're told that you've got a hyperbola and it's got an eccentricity of root 2. Now, if it's got an eccentricity of root 2, that's a very specific hyperbola, which means it's a rectangular hyperbola. But the question doesn't want you to use the sort of starting standard Cartesian form of any hyperbola to solve this. They want you to use the locus relationship, which is the relationship between the distance of a point on the hyperbola and the ratio between that distance and the directrix and that distance and the focus. So on the graph, the green curve there is the hyperbola that we're working with. We're told that the focus is this line x plus y equals k. So it's going through the k coordinate on the y-axis and the k coordinate on the x-axis as well. And the focus, which is 2k comma 2k, is lying on the line y equals x. So basically what's happened is that it's taken a standard rectangle hyperbola and it's kind of rotated it through 45 degrees. So your standard one looks like that, with asymptotes going through the origin, and it's taken that, it's kind of twisted it through 45 degrees. So what this wants us to do is to, as I said, the question's asking us to use the locus definition, which is all to do with this eccentricity. So what we're doing is we're looking for the ratio of that distance PS compared to the perpendicular distance to the directrix, which I'll call PE. PS over PE equals the eccentricity of the shape. So that is the ratio that will actually get us a line of maths that we can use. So the distance PS over the distance PE equals the eccentricity, and in this very specific case with a rectangular hyperbola, the eccentricity is equal to root 2. For other ones, if the eccentricity is between 0 and 1, you get an ellipse. If it's greater than 1, you get a regular hyperbola. But for the specific instance where it's a rectangular one, the eccentricity is root 2. Right, so what I'm going to do now is lift out of this. What we've got are a pair of right angle triangles that we can use to get the distances PS and the corresponding distance here PE. So if I work with that one first of all, so if I lift that out so it's easier to see, not with a green pen is it easier to see. So that's P, and I call it capital X, capital Y. This is S, which has got the coordinate 2k, comma 2k. So I can use those coordinates to work out what this horizontal distance is going to be. It's going to be 2k from the origin there, x from the origin there, so that distance is going to be 2k minus x. And similarly here, we're going to have y minus 2k. So using Pythag, I can get an expression for PS. Is going to be that squared plus this squared. So PS squared Squaring out that, you get y squared minus 4ky plus 4k squared. For the second bracket, I get plus 4k squared minus 4kx plus x squared. Tidy that up a little bit. I got x squared plus y squared, and then I've got 4kx, 4ky, and I've got 8k squared. So that gives me an expression for PS. Now I've got to look at this triangle for PE. So P, capital X, capital Y. I know it's a right angle triangle, and the E coordinate, because I've got this equation in the form x plus y equals k, then the x coordinate is x, and the y coordinate can be written as k minus x. Yeah, just by rearranging that, y equals k minus x. So the problem that we've got here is I've got the capital X, which is defined as a coordinate on our curve, but as that point moves, the coordinates of that value, that point, change as well, which is why it means that I've introduced an additional coordinate, additional variable, x. I can write the y in terms of it, so I don't have to put an extra y coordinate in there, but nevertheless I've got an x, a lowercase x there, which is a pain in the butt and I need to be able to deal with. If we look at how this pans out as far as the sides are concerned, then what we will have is that this side will be capital X minus little x, and this side will be capital Y minus this y coordinate, which is k minus x. So capital Y minus k plus x. So this problem that we've got to deal with now is the fact that we've introduced an additional variable. So if I was to use Pythag now, then I'm going to have another coordinate in there which I don't want to have. Fortunately, if we go back and look at the sketch that we've got here, you should be able to see that the gradient of y equals x is 1, and the gradient of this, if I rearrange that to give me y equals minus x plus k, I can see that the gradient of this is negative 1, which means that these two lines are perpendicular to each other. That's the line y equals x, and this is the line y equals minus x, but it's been shifted, been transformed along the axis. So as that point moves, because I'm working with the perpendicular distance to the directrix, that means that this line is always going to be parallel to the line y equals x. So it means that this gradient is always 1. And if that gradient is always 1, it means it's at 45 degrees. So I can establish that that angle there is 45 degrees. Okay, because it's always parallel to the line y equals x. Now because of that, I can use trig to say opposite over adjacent, opposite y minus k plus x over adjacent x minus little x equals opposite of adjacent tan of 45, and tan of 45 is 1. So this is going to enable me to get x in terms of y and k, and big X. So y minus k plus x, bringing that up, x minus x. Take that minus x to make it positive and chuck those over the other side. I get 2x equals big X minus y plus k. So x equals x minus y plus k all over 2. So what I've done now is defined that coordinate as it moves along the directrix purely in terms of x, y, which is the coordinates of that point, and k, which is the position of that as it runs up and down the y-axis. So now that I know that, I can rewrite that there So if I draw that again now, just to make it easier to keep track of. So I got my P, X, comma Y, and I've got my E here, and this is now X minus X, and X minus X equals big X minus, and little x is that. So X minus Y plus K all over 2. Bring those together. If I want them all over 2, I'll get 2x minus x plus y minus k all over 2, which is x plus y minus k all over 2. Now I know that that's 45 degrees. So I could do the same with that and use Pythag, or because I want PE and I now know that side and an angle, I can use right angle trig. So there's different ways from here. Hypotenuse adjacent, so that over that is cos 45, adjacent over hypotenuse. X minus x over PE will be cos of 45. So x minus x equals PE cos 45. X minus x I've worked out is that. Put that there. So x minus x is that. So x plus y minus k all over 2 equals PE, and cos of 45 is 1 over root 2. So PE is root 2 over 2 x plus y minus k. Right, so let's go back to our original relationship. This was the locus definition of a hyperbola. PS, well, I got PS squared as that, over PE, which is that, equals E, and the question tells me E is root 2. So now PS over PE equals E equals root 2. PS equals root 2 PE. Now, because I don't want to be working with that as a square root, and I have that squared, life is going to be easier if I square everything. PS squared equals 2 PE squared. Well, I got PS squared as an algebraic string there. So if I work out what this is first, just to keep the lines short enough, PS squared equals 2, and then PE is that all squared. So when I square that, I get 2 over 4 x plus y minus k times x plus y minus k. 4 over 4 is 1, so that's gone. So I get PS squared. Expanding this, I've mixed my x's up there, there's both capital X's. So it's x times x is x squared. X times y is xy. X times minus k is minus kx. Then I'm into the y term. Y times that is xy. Y times that is y squared. Y times that is minus ky. Then I'm into the k term. So minus kx minus ky plus k squared. So PS squared is x squared, only one of those. Y squared, only one of those. I have an xy and an xy, 2xy. Then I have minus kx minus kx minus 2kx, and a minus ky and a minus ky minus 2ky. So I have PS squared is equal to that. Yes. So PS squared, I've done the 2PE squared on this side. So now I can bring PS squared I derived over there. So therefore, I got this PS squared, which is from there, x squared plus y squared minus 4kx minus 4ky plus 8k squared equals the PE squared term that I've got there. And I've just noticed that I've left off the plus k squared. So the plus k squared. Okay, well, we just now need to tie this all together. So the x squareds and y squareds are going to go because they're the same on each side. I've got 2xy on that side. Then I've got negative 2kx, my x's and y's are starting to look the same. Negative 2kx there. When that negative 4 comes over, it becomes positive. So I get 4kx, take 2kx is plus 2kx. So that's dealt with that and that. Same with the ky. When I bring that one over, it's a 4ky. Sorry, it's not the ky, that's the kxy. So I got the 4ky, take 2ky is plus 2ky. And then to get the same as the answer, I'll bring the k squared from there over there. I have 8k squared, take away 1k squared, which is 7k squared, which when we have a look at what the answer was in the book, 2xy plus 2kx plus 2ky equals 7k squared. So I would be astounded if you got a question like that on a further maths A-level paper. Keyword that your dad missed out there, which made it really difficult to start, because you were looking at the various forms of eccentricity and locus and directrix, standard results that you could use, and they didn't really help you with that. But that was a really tricky question. As I said, I haven't seen anything like that in Edexcel, or when I was doing that as part of the WJC further maths with a student in Milford last year. So I wouldn't worry about it if you can't follow that.